Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about the Sommerfeld expansion, which is basically a method to work with the integrals that we found where we multiply densities of states, or later also other things like an energy times the density of states times the Fermi function. So what we saw before is that we want to calculate the integral over the densities of states times the Fermi function. And we'll later encounter integrals where we multiply with the energy to get the total energy, or other functions to get other properties of that system. I integrate from minus infinite. Of course, in the Sommerfeld model you can integrate from 0. But in the Sommerfeld model, if you say that the densities of states for negative energies is 0, it doesn't matter if you integrate from minus infinite or from 0 to infinite. And we want to express this integral in something else than polylogarithmic functions. Especially if you want to do series expansions around t is 0 of a polylogarithmic function, you will find that your Taylor series has a convergence radius of 0. So that's all not so nice if you want to look at low temperature behavior. And what we will use is that our Fermi function has a symmetry. If x is the energy away from the chemical potential, then we can express the Fermi function for mu plus x and mu minus x as f mu plus x is 1 minus f mu minus x. So we're going to look at this integral, and we're going to integrate once the densities of states without the Fermi function up to the chemical potential, and then we have an integral from the chemical potential up to infinite of dE Fe. And then we have to subtract the integral without the chemical potential, and we have to add the integral of the densities of states times the Fermi function, dE. This is the integral over the densities of states up to the chemical potential plus. And now I'm going to make a substitution where I'm going to replace the energy by the chemical potential plus x. So mu becomes 0 for x, infinite stays infinite, d mu plus x, f mu plus x dx minus, and now I'm going to here replace the energy by mu minus x dx. So integration boundaries, because I have a minus sign in here, flip, so mu becomes 0, minus infinite becomes plus infinite, and I have d mu minus x 1 minus f mu minus x dx is the integral minus infinite to the chemical potential of the densities of states plus. And now I have here 2 times the same integral in terms of boundary conditions and dx. I have an d mu minus x and a d mu plus x. And I can use that 1 minus f mu minus x is f mu plus x, such that we have f mu plus x dx. As a next step, we're going to expand in the densities of states around the Fermi energy. And we're going to expand in X around X is 0. So d mu plus X minus d mu minus X is given by the sum n is 0 to infinite 1 over n faculty. And this is just a Taylor series expansion. We take the derivative of mu plus X minus d mu minus X, and then the nth derivative with respect to X evaluated in the point X is 0, X to the power n. Now, this is an odd function in terms of X, so I only have to look at the odd derivatives. So I can make the sum n is 0 to infinite, and I only have to look at cases where this is an odd number, d 2n plus x, and this is the derivative of the densities of states evaluated in the point where x is equal to the chemical potential. X to the power 2n plus 1, as we're only interested in the odd derivatives. So with that, we find that the integral that we wanted to evaluate of the densities of states times the Fermi function is equal to an integral up to the chemical potential of the densities of states plus a series 1 over 2n plus 1 faculty, and then the derivative of the densities of states, or the 2n plus 1 derivative of the densities of states evaluated at the chemical potential times an integral 0 up to infinite x to the power 2n plus 1 times the Fermi function of x plus the chemical potential dx. Let's have a look at this integral, and the Fermi function evaluated at x plus the chemical potential is a function where the chemical potential drops out, e to the power x divided by k Boltzmann t, and the integral over that function x to the power 2n plus 1 divided by 1 plus e to the power x divided by k Boltzmann t dx is again one of the standard integrals that you can find in books with tables of integrals, whereby I really wonder if anybody of you ever went to a library to look up such a book. If not, Mathematica immediately does this, so as Maple or other functions or software packages that have these books nowadays as libraries. Internal, 1 minus 2 to the power minus 2 minus 1 times k Boltzmann t to the power 2n plus 2, 2n plus 1 faculty, and then the Riemann zeta function 2n plus 2. So we have an exact expression for this integral in terms of a series that includes the odd derivative of the densities of states multiplied with, and this is just a number. Now let's make some approximations. And the first approximation that we make is that we only go up to first order. So we only look at the derivative and not at the higher order derivatives of the densities of states and the chemical potential. Which means we have to go to n is 0 because I took 2n plus 1 as my derivatives. So we find that the integral that we want to evaluate of the densities of states times the Fermi function is roughly minus infinite up to the chemical potential of the densities of states dE plus, and we can now look at the Riemann-Zeta function giving me a pi square and all the other constants over 6 k Boltzmann t to the power n is 0, so that is the power 2, and then we have the first derivative of the densities of states evaluated at the chemical potential. Now we can make a further approximation, and we can, instead of the chemical potential, look at the Fermi energy. But this is something I want to correct, so I have to add the integral of the densities of states from the Fermi energy to the chemical potential. So far that's not an approximation yet, but now I'm going to make an approximation. Here I already look at the derivative of the densities of states, so that's already a first order, and then I can change here the chemical potential by the Fermi energy. Pi square over 6 k Boltzmann t square The correction is small, so the error in the correction is even smaller. Well, this integral is just the number of particles. And this integral, when the Fermi energy and the chemical potential are close to each other, I can look at this as the length of my integration path, and the densities of states will be constant, so I can look at the densities of states at the Fermi energy. And it's constant because my integration length is just very small. And the last term stays the same because we already made the approximations that we want to make here. At the Fermi energy. With this, we can put in the values that we have in the Sommerfeld model and actually find an expression for the chemical potential as a function of temperature. We know that the Fermi energy is 3 pi squared n to the power 2/3 h bar squared over 2m, which is a result we obtained in one of the previous lectures or videos. And we know the densities of states, the Fermi energy, which is 1 over 2 pi squared, 2m over h bar squared, to the power 3/2, and then the square root of the Fermi energy. Actually, we need a derivative in there. If you put this all in, then you find that the chemical potential as a function of temperature is 1 minus pi squared over 12 k Boltzmann t divided by the Fermi energy squared times the Fermi energy. So we find that indeed the chemical potential goes down as a function of temperature. It goes down parabolic, so at 0 temperatures the change is 0, and at higher temperatures it scales down in this fashion. And that is of course a much nicer result than the polylogarithms that we had before. Similar derivations can be made when it's not just the densities of states, but it's the densities of states times a polynomial in the energy that is just going to change expressions in x here, and those are all analytical solvable integrals, so you just get different prefactors. And it is those integrals that we will need at some point later in this lecture. I will not do them in that lecture anymore. We went through the math here once. You either be able to do them yourself or open a program like Mathematica and they can do all these integrals and make plots of them. If you end up with polylogarithms, they are relatively nasty functions if you want to look at the behavior at low temperature, because you can't make simple Taylor series expansions of those. Thank you very much for your attention. That's why we have, of course, the Sommerfeld expansion. Yeah, thank you very much for your attention. In the next videos, we'll have a look at some physical properties that we now can calculate within the Sommerfeld model. Simple things like Ohm's law, but also specific heat or the ratio of thermal conductivity to electric conductivity. We'll see each other next time. Stay healthy.